All right, so I'll be presenting about non-adiabatic couplings of the first and second order for orbitals and excitons, and there'll be some similar stuff to what Lola talked about since she addressed non-adiabatic couplings. Um, so as for what they are, it's a coupling between the electronic and nuclear degrees of freedom. And in the case of nuclear degrees of freedom, that can relate to like vibrational degrees of freedom. And in this case, since it's non-adiabatic, the nuclear degree of freedom is not approximated as adiabatic, and I'll explain a little more about that in a moment. So, why do we consider non-adiabatic couplings? Whenever we're solving dynamics of some quantum system, we like to use the time-dependent Schrodinger equation, but it can be pretty difficult to solve depending on what your wave equation is, especially if you have a lot of ions or electrons in your system. So, something we like to do in computational chemistry is to use the Born-Oppenheimer approximation, which will separate the electronic and nuclear wave functions. And then the nuclear wave functions are treated as adiabatic, or essentially like it's not moving in space, its positions are fixed, and the electrons move about how they will. The advantage of using this Born-Oppenheimer approximation is that it's computationally more efficient, it simplifies your equations, and also you can like simulate molecular dynamic trajectories in a classic way. The disadvantage of doing molecular dynamics in this classic way is that there may be quantum effects you're not accounting for, like tunneling or 0-point energy. And we also like to consider non-adiabatic couplings for things like photoexcitations, because like your ions will move around, and we want to see how that affects your trajectories. So to construct the non-adiabatic couplings for single orbitals, for starters, instead of splitting up the electronic and nuclear degrees of freedom, we're going to express our total wave function as a linear combination of the electronic adiabatic states and some coefficient. And if you put this ansatz into the time-dependent Schrodinger equation, we're going to have our diabatic coupling term, which is this VK, and the non-adiabatic coupling vector. And that's been explored by Lola. So in the process of obtaining these expansion coefficients, as discussed, we want to find what the probability amplitude of these coefficients are and fewest switches surface hopping, so that way you can know the probability of a state transitioning occurring between some different time steps. But then going back to finding this coefficient, you can do some renaming of how you call your coefficient and the diabatic term. We get our time-dependent Schrodinger re-expressed, and then since we want to integrate it, and we're going to be integrating it computationally, since we're going to probably be doing simulations on a computer, you can use the fourth-order Runge-Kutta numerical integration method. And in the process, this C tilde coefficient that we've renamed, it'll contain all the information, so you don't have to worry about going back to finding that C of j. And since we're in Runge-Kutta integration approximation, we get a second-order derivative. We've moved on to second-order non-adiabatic coupling. We could also rename our non-adiabatic coupling vector like so. And with that, we get this final expression for the non-adiabatic coupling vector. And that can help us find what our coefficients are. And note that we have, for these electronic adiabatic terms, we have two different time steps. So if you've done non-adiabatic couplings, you'll note that you at least need two different time steps to get a calculation. So if we want to move on to excitons, which are, in brief review, it's a quasi-particle that's an electron-hole pair. It can be useful to look at electrons if you're looking at things like singlet fission or some charge dynamic situations. And the difference between orbitals and the excitons is, instead of having our single orbital exciton wave function, we use the Slater determinant basis, which will be made up of these adiabatic electronic structures, which they could be like represented as one electron conjugate orbitals. So move on to that. You can express the Hamiltonian in terms of this determinant basis, and from I know this can connect to how you construct your non-adiabatic vector. And so once you have your Hamiltonian, we get this similar looking expression to before with the Runge-Kutta expression for the numerical integration. So you can solve what your non-adiabatic coupling vectors or your transition dipoles are at different time steps. And if we want to connect this all to non-radiative relaxation, since we're interested to see our system evolves over time. Like we talked about, if you have your coefficients and you know the probability of them transitioning, then you can know how many are in a certain population. So supposing you're in surface hopping, you can have your number of orbitals, or I guess exciton pairs that are in a certain state, and then you can see how the population will change over time. And I guess another item of note, in the process of solving our nonadiabatic coupling equation, we are able to symmetrize our equation, and that's an important feature since that makes the integration, it makes your system time reversible, which is important for the integration setup we do, and also having a time reversible situation is important for detailed balance. So, all right, that's my presentation. I'll leave it up for questions.